Okay, YouTube, in this video I'm going to continue my exploration of writing equations of lines and using equations of lines to make what we would maybe consider to be accurate predictions. But in this video we're going to focus on what we call lines of fit, and especially lines of best fit. And so considering data, we say data do not always show an exact linear relationship, but we do say that sometimes when data in a scatter plot show an approximately linear relationship, we can actually model that data with a line of fit. So just kind of as an example, if we were to consider a situation where if we said, okay, well, let's find the correlation between two variables or a connection between them. Maybe we say the person's length of leg, so leg length. Maybe we plot down on this axis here. We measure a bunch of people's legs, and then we have them run the mile, like mile time. We put that up here. We could say that maybe the data does this. The shorter the person's legs, we say maybe it takes them a while to run the mile here, but we get maybe some sort of relationship that would show something here that is approximately linear in the sense that the longer a person's legs get, the faster they can run the mile time. So our goal will be to come up with what we call a best fit line, but in this case we're going to use just a line of fit. So what we'll do is create a scatter plot for the data, which is our first step here, and I'm kind of hypothetically kind of mapping this here, but we say sketch the line that most closely appears to follow the trend given by the data points. And what we're going to do is we're going to try to find the equation of that line and use it to make some predictions either outside the data set or inside the data set. We refer to those as extrapolation and interpolation respectively. But in terms of a line of best fit, if I said, well, does this line here, describe the data very well? And I would say, well, not really. If I had to choose a line of best fit, I would probably choose one that kind of is the closest, to all the points as it possibly can, the best fit here. So if this were, say, a line here, basically what I could do is I could say, well, let's find the equation of this line, and our method will just be this. We're going to choose 2 points that are really close to the line. I notice there's a point there really close to it, and maybe this point right here, and use that to find, first of all, the slope. And once we have the slope, we'll also find, use one of these points. We could say use this as our x1 and our y1 here, and essentially we could use our point slope formula, which says if we know a point and some slope of some line, we could write its equation by saying y minus y1 of our point equals the slope times x minus x1 of our point. So that method is going to allow us to make some predictions. So you'll notice that I've kind of got an example here that I've taken screenshots from, and this is going to save us a little bit of time, but it says that the following table here shows the connection between femur lengths in centimeters for a person, and as well as their heights, of several different people. So if we were to actually plot this data in a scatter plot, you'll notice that we already have a scatter plot listed over here. You can see that the data aren't exactly in a line, but there is certainly a connection between how long somebody's femur is and how tall they are if we're measuring both of these in centimeters in this particular instance. So we say, do the data show a linear relationship? Well, I say they approximately do. So we say, if so, let's write an equation of a line of fit and use it to estimate the height of a person whose femur is 35 centimeters long. Now, I'm not saying that we can't just go over here to this graph and say, well, 35 lies, medial to 30 and 40. But we'd say, if I were to trace this up here, we could get a good guess kind of from the data set here about how many centimeters tall this person is. But what we want to do is be very accurate. So you'll notice here, step 1 was create the scatter plot for the data. Now, if I didn't already have this graphed, I would actually have to go make my own graph, okay? And so they have made a graph here, the people that provided me with this. Step 2 would be to sketch the line that most closely appears to fit the data. Well, here's our line of fit. It kind of, goes through as many of the points as we possibly can here, as closely as possible, approximating the relationship between femur length and height. Since that's done, though, what we're going to do is we're going to write the equation of this line. Now, what do we know about the equation of a line? We need the slope, and we also need a point on the line. So here's the method. We're going to use 2 points that are closest to the line, and then we're going to use those points to approximate the slope of the line. Afterwards, we're going to use that slope as well as one of those points to write the equation of a line. So in this particular instance, we're highlighting 2 points here that happen to be very close to this line here, 40 centimeters, 170 centimeters, and 50, 195 respectively. So to find the slope, remember slope is change in y over change in x. So I'm going to say 195 minus 170 here. It's our y2 minus y1, and then we'll take 50 minus 40 for our change in x. And what we end up with here is a slope of 25 tenths. In other words, we get 2.5. Okay, 2.5. I'm going to put a box around this. So to write the equation of the line, what we'll do is we'll just select one point from the entire data set. We could use any point that we want to use. As a matter of fact, I'm going to choose to use 40, 170 because I already know this here. But to write its equation, recall that we can just use this point slope formula and say it's y minus the y value of our point, which in this case is 170. This is equal to the slope. So we have the slope here, and the slope is 2.5. That was easy to determine. And then we say, okay, well, now we've got x minus some x value of our point, where the x value of our point you can see up here is 40. So this is essentially the equation right here. We don't have to simplify it, but it is certainly a standard thing to do. So if I distribute the 2.5, I get 2.5x. We say 2.5 times negative 40, that's going to be negative 100. And if I add 170 to both sides here, 170, essentially we get a line here, an equation of a line that says that y is equal to 2.5 times x plus 70 when simplified. So here's our equation that relates y, which is our height, to the femur length, which is our x. So the question we were trying to answer in the first place was, how tall is a person if we know that their femur is 35 centimeters long? And we could at least get a good approximation. So since we were given a femur length, keeping in mind femur length is x here, what we'll do is we'll say, let's go evaluate for y when x is equal to 35 centimeters. So essentially what we'll do is we'll plug this in. We say 2.5 of these 35 centimeter things plus 70. This is going to give us an approximate height. So if we were to say, let's get our calculator out here, we'll quit out of this. Quit. And we say, all right, well, I want 2.5 times 35 centimeters plus, and we have 70. We get a value of 157.5 centimeters. So we would say y is 157.5 centimeters according to this. And all I want to do is check this reasonability above here. So notice if we had gone up to 35 centimeters and traced it up and over, I would have landed right in here somewhere. And I say, well, if this is 160 and this is 80, this is 120 in between those. So, to say it's 157.5, it's really close to 160, this graph only verifies that. So, in this example, we looked at a line of fit. In this next example here, I want you to bear with me. We're going to use our graphing utility to come up with what we call a line of best fit. So, I write here, it says the line of best fit is a line that lies as close as possible to all the data points. We can actually do this using technology. So if your technology tool, which our calculators have here, a tool that's called a linear regression, but if they have a linear regression feature, then we can actually use that to find not just an approximate line, but like the best fitting line for all of the data. So I'm going to walk us through how we do this on a calculator, and I'll get my calculator out here. But the steps you need to play around with in order to get this to work. So the very first thing we need to do is actually put all the data in a table. Okay, so the first thing you'll do is you'll turn your calculator on, and we're going to head to Stat. Now once you pull up Stat, we've got certain submenus here. We're going to go to Edit, and the very first option says Edit. I'm going to click on Enter. Now what I want everybody to notice first off is that I've already put in a bunch of data. As a matter of fact, I just got this from the other page. All I have to do, for instance, here is hit 40, Enter, and then it's just going to keep going down. But we'll put in all of our femur data on one side. Okay, and it is very important that we put in all of our height data that went with that femur data on the right side. So that is if somebody has a femur length of 40 centimeters, that was the person that was 170 centimeters tall. But you should have just as many data on the right as we have on the left. We can see that we have that as the case. Okay, so the first thing we do, recall, is we go to Stat, Edit, and we put in the data into the two lists. Once those are in, though, what we're going to do is use the linear regression feature. So essentially, once that data is entered, notice I say press the Stat key again and scroll right to the Calc option and then down to the fourth option that says Lin Regression. You notice this doesn't say mx plus b, but some ax plus b. They're using a in place of m. So again, if I click on Stat, notice that there's this Calc menu here. Once you have all your data in, you go to Calc, and this is the linear regression that we want. We want to find the line of best fit. So when I go down here and I click on Enter, the first thing that happens is this pops out to the main page. Nothing has happened yet, but when I hit Enter, the coolest thing happens. If there is a linear relationship between these two variables, what it's going to do is say, well then, if you had a line of best fit, its equation would be y equals ax plus b, where a would be approximately this and b would be approximately this. And you notice that I said approximately because this is, I can't use the exact value of all these. So I'm going to say a is 2.6 and b is 64.996. We'll call it 65. So we'd say a is approximately 2.6 and we say b is approximately 65. Using this though, I say let's go graph the regression equation in the scatter plot. What I want to do is just go ahead and write the equation of our line. So if it's ax plus b and we have these values, then really the equation of our best fit line is approximately 2.6 as a slope plus 65 here, and this would be our equation that we're going to use to figure some things out. Now, when I say let's go graph the regression equation into our calculators, remember to graph something we have to go to our y equals menu, which is our top left button here. And we're just going to put in this equation. We're going to say 2.6x. In this case, we have plus 65. Now, I will say this. When we graph this, we're not going to be able to see it. And the only reason I say that is because recall, at least from our last figure here, that this graph is, the highest x value went out to, it looks like 50 here I'm seeing. And the biggest y value goes up to 195. So what we're going to do is we're going to, for the first time probably, need to change the window that we're looking at here. So to change the window, we're going to go to this feature that says window. And essentially what I want everybody to see here is this. When you change your window, I'm going to point this out. Your calculator is going to say what's your x min, what's your x max. Really what it's saying is what is the leftmost x value and what is the rightmost x value that you want to go out to. Likewise, we have a y min and a y max option. And we're going to change those to reflect the values that we want to show in our graph. Furthermore, it's also going to ask us what we want our scale to be. When asking about scale, I notice here on the x-axis that we're going by units of 5, okay? So we can change the scale to fit our needs. So I notice that this graph goes from 0 out to 60 on the x-axis and from 0 up to about 200 on the y-axis here. So what I'm going to do is I'm going to say my x min is 0, and I'm going to hit enter. X max, I can just type this in. I can say x max is, we went out to 60 on this graph over here. And then our scale, why don't we go by 5s to adopt the same scale we have on this graph here. As far as y min, we're going to start at 0. We said we're going to go up to 200, okay? And we'll go by, how about we go by, it looks like we're going by 40s over here, so 40. Once we have this in, we can go ahead and hit graph, and we'll be able to see this relationship here. And this is kind of a very, very neat thing to play around with. The other thing I want everybody to do is actually go back into y equals, and up at the top you see plot. And if we go up here to plot 1 and we actually hit enter, you'll notice, I'll scroll off of this, it highlights it. And that plot 1 is really just the plot of data from this list. If you don't highlight that, it won't show up. But if I hit graph now, notice that all those data points that I'm seeing over here are showing up, and here's our line of best fit. So if we wanted to make some approximations here, I put some directions down here, but it says use the trace key to pull up your trace bullseye, and then hit either up or down to make sure that you're on the graph of the line, okay? So I'm going to find this trace key first. This is a really neat feature. Now, when I say hit up or down to be on the equation of the line, right now it says, I don't know if you can see this bullseye right here. It's blinking. It says you're at 40, 170. And that's actually one of our data points. It's this first one you see here. But at the top left, it says you're on the plot 1. What we want to do is hop down to the graph. So if we hit up and down, I want you to see this. It goes to y1 equals 2.6x plus 65. And if I hit down again, it pops back to the plot. And if I hit down again, it pops the line. We want to be on the line. And from here, we can hit left and right. And the nice thing about this is you can see it crawling along the graph. And it says, well, you're approximately about 22.97 centimeters, 125.74 centimeters. The question we are trying to answer is this. If a person has a femur that is 35 centimeters long, approximately how tall are they? So we're going to do this in 2 methods. One is we're going to actually scroll over to about where we think 35 would be for an x value, getting as close as we possibly can. So I say close to this, I can see about 156.27 centimeters. Now, not bad considering that our approximate line here gave us about 157.5. But using our best fit line equation, now what we can do is we can not only use our trace feature here, we can actually find an exact value using this line. So one way to do this is to plug it into the equation, 35 for x. The nice thing about the trace feature is if I just hit 35, then it says when x is 35, hit enter. It says, well, then your y value is exactly 156, which again, the approximate line was about 156. The best fit line says, well, really, really close to 156. So the last thing I'll mention here is this. If we had a best fit line, we could actually just go ahead and plug this in for the x value here. And we'd say, okay, well, using my calculator, I'll go to second mode, which is our quit option here, and I'll clear this out. But I'd say 2.6 times 35 centimeters plus 65, and this would be the same output that our calculator had just mentioned before. So we'd say, using the best fit line, 156 centimeters would be the approximate height of a person who has a femur size of 35 centimeters, given the data set that we had seen.